In France, for example, tidal currents that accompany a high tide of 12 meters may attain a speed of 20 kilometers per hour. While tidal currents are not generally major agents of erosion and sediment transport, notable exceptions occur where tides move through narrow inlets. Here they constantly scour the small entrances to many good harbors that would otherwise be blocked. Did you know? The world's largest tidal range is found in the northern end of Nova Scotia's Bay of Fundy. Here the maximum spring tidal range is about 17 meters. This leaves boats high and dry during low tide. Sometimes deposits called tidal deltas are created by tidal currents. They may develop either as flood deltas landward of an inlet or as ebb deltas on the seaward side of an inlet. Because wave activity and longshore currents are reduced on the sheltered landward side, flood deltas are more common and more prominent. They form after the tidal current moves rapidly through an inlet. As the current emerges from the narrow passage into more open waters, it slows and deposits its load of sediment. As a rapidly moving tidal current moves through a barrier island's inlet into the quiet waters of the lagoon, the current slows and deposits sediment, creating a tidal delta. Because this tidal delta has developed on the landward side of the inlet, it is called a flood delta. Such a tidal delta is shown in Figure 17.14a. Figure 17.35 Tidal deltas. Concept check 17.7. 1. Explain why an observer can experience two unequal high tides during a single day. 2. Distinguish between neap tides and spring tides. 3. Contrast flood current and ebb current. Concepts in review, shorelines. 17.1 The shoreline and ocean waves. Explain why the shoreline is considered a dynamic interface. List the factors that influence the height, length, and period of a wave and describe the motion of water within a wave. Key terms. Shoreline interface: wave height, wavelength, wave period, fetch, surf. The shoreline is a transition zone between marine and continental environments. It is a dynamic interface, a boundary where land, sea, and air meet and interact. Energy from waves plays an important role in shaping the shoreline, but many factors contribute to the character of particular shorelines. Waves are moving energy, and most ocean waves are initiated by wind. The three factors that influence the height, wavelength, and period of a wave are wind speed, length of time the wind has blown, and fetch, the distance that the wind has traveled across open water. Once waves leave a storm area, they are termed swells, which are symmetrical, longer wavelength waves. As waves travel, water particles transmit energy by circular orbital motion, which extends to a depth equal to 1/2 the wavelength. When a wave enters water that is shallower than the wave base, it slows down, which allows waves farther from shore to catch up. As a result, wavelength decreases and wave height increases. Eventually the wave breaks, creating turbulent surf in which water rushes toward the shore. 17.2 Beaches and shoreline processes. Explain how waves erode and move sediment along the shore. Key terms. Beach abrasion, wave refraction, beach drift, longshore current, rip current. A beach is composed of any locally derived material that is in transit along the shore. Waves provide most of the energy that modifies shorelines. Wave erosion is caused by wave impact pressure and abrasion. As they approach the shore, waves refract to a line nearly parallel to the shore. Refraction occurs because a wave travels more slowly in shallower water, allowing the part still in deeper water to catch up. Wave refraction causes wave erosion to be concentrated against the sides and ends of headlands and dispersed in bays. Waves that approach the shore at an angle transport sediment parallel to the shoreline. On the beach face, this longshore transport is called beach drift, and it is due to the fact that the incoming swash pushes sediment obliquely upward, whereas the backwash pulls it directly downhill. Longshore currents are a similar phenomenon in the surf zone, capable of transporting very large quantities of sediment parallel to a shoreline. What process is causing wave energy to be concentrated on the headland? Predict how this area will appear in the future. 17.3 Shoreline features. Describe the features typically created by wave erosion and those resulting from sediment deposited by longshore transport processes. Key terms: wave-cut cliff, wave-cut platform, marine terrace, sea arch, sea stack spit, Behemoth Bar, Tombolo Barrier Island. Erosional features include wave-cut cliffs, wave-cut platforms, and marine terraces. Erosional features also include sea arches and sea stacks. Some of the depositional features that form when sediment is moved by beach drift and longshore currents are spits, behemoth bars, and tombolos. Along the Atlantic and Gulf coastal plains, the coastal region is characterized by offshore barrier islands, which are low ridges of sand that parallel the coast. Identify the lettered features in this diagram. Figure 17.9-1 Full alternative text description. 17.4 Contrasting America's coasts. Distinguish between emergent and submergent coasts. Contrast the erosion problems faced on the Atlantic and Gulf coasts with those along the Pacific coast. Key terms: emergent coast, submergent coast. Estuary. Coasts can be classified by their changes relative to sea level. Emergent coasts are sites of either land uplift or sea level fall. Marine terraces are features of emergent coasts. Submergent coasts are sites of land subsidence or sea level rise. 1. Characteristic of submergent coasts is drowned river valleys called estuaries. In the United States, the Pacific coast is emergent, and the Atlantic and Gulf coasts are submergent. The Atlantic and Gulf coasts of the United States are lined in many places by barrier islands, dynamic expanses of sand that see a lot of change during storm events. Many of these low and narrow islands have also been prime sites for real estate development. The Pacific coast's big issue is the narrowing of beaches due to sediment starvation. Rivers that drain to the coast have been dammed, resulting in reservoirs that trap sand and prevent it from reaching the coast. Narrower beaches offer less resistance to incoming waves, often leading to erosion of bluffs behind the beach. What term is applied to the masses of rock protruding from the water in this photo? How did they form? Is the location more likely along the Gulf Coast or the coast of California? Explain. 17.5 Hurricanes, the ultimate coastal hazard. Describe the basic structure and characteristics of a hurricane and the three broad categories of hurricane destruction. Key terms: hurricane eye, walleye, storm surge. Hurricanes are fueled by warm, moist air and usually form in the late summer when sea surface temperatures are highest. Water vapor in rising warm air condenses, releasing heat and triggering the formation of dense clouds and heavy rain. Because of a steep pressure gradient, air rushes into the center of the storm. The Coriolis effect and ocean water temperatures strongly influence where hurricanes form. The eye at the center of a hurricane has the lowest pressure, is relatively calm, and lacks rain. The surrounding eye wall has the strongest winds and most intense rainfall. The Saffir-Simpson scale classifies storms based on their air pressure and wind speed. Most hurricane damage comes from one or a combination of three causes: storm surge, wind damage, or inland flooding due to heavy rains. Storm surge is ocean water that gets pushed up above the normal water level by the strong winds. In the northern hemisphere, hurricanes rotate counterclockwise, and storm surge is greatest on the right side of an advancing hurricane. This is due to the combination of the storm's forward movement and strong winds blowing toward the shore. This coastal scene shows hurricane destruction. Which one of the three basic classes of damage was most likely responsible for this destruction? What is your reasoning? 17.6 Stabilizing the shore. Summarize the ways in which people deal with shoreline erosion problems. Key terms: hard stabilization jetty, groin breakwater, seawall. Beach nourishment. Hard stabilization refers to any structures built along the coastline to prevent movement of sand or shoreline erosion. Jetties project out from the coast with the goal of keeping inlets open. Groins are also oriented perpendicular to the coast, but their goal is to slow beach erosion by longshore currents. Breakwaters are parallel to the coast but located some distance offshore. Their goal is to blunt the force of incoming ocean waves, often to protect boats. Like breakwaters, seawalls are parallel to the coast, but they are built on the shoreline itself. Often the installation of hard stabilization results in increased erosion elsewhere. Beach nourishment is an expensive alternative to hard stabilization. Sand is pumped onto a beach from some other area, temporarily replenishing the sediment supply. Another possibility is relocating buildings away from high-risk areas and leaving the beach to be shaped by natural processes. Based on their position and orientation, identify the 4 kinds of hard stabilization illustrated in this diagram. Figure 17.9-1 Full alternative text description. 17.7 Tides. Explain the cause of tides and their monthly cycles. Describe the horizontal flow of water that accompanies the rise and fall of tides. Key terms: tide, spring tide, neap tide, tidal current, flood current, ebb current, tidal flat, tidal delta. Tides are daily changes in ocean surface elevation. They are caused by gravitational pull on ocean water by the moon and, to a lesser extent, the sun. When the sun, earth, and moon all line up about every 2 weeks, the tides are most exaggerated. When a quarter moon is in the sky, it indicates that the moon is pulling on Earth's water at a right angle relative to the sun, and the daily tidal range is minimized, as the two forces partially counteract one another. A flood current is the landward movement of water during the shift between low tide and high tide. As high tide transitions to low tide again, the movement of water away from the land is an ebb current. Ebb currents may expose tidal flats to the air. If a tide passes through an inlet, the current may carry sediment that gets deposited as a tidal delta. Give it some thought. 1. During a visit to the beach, you and a friend get in a rubber raft and paddle out into deep water beyond the surf zone. Tiring, you stop and take a rest. Describe the movement of the raft during your rest. How does this movement differ, if at all, from what you would have experienced if you had stopped paddling while in the surf zone? 2. Examine the aerial photo that shows a portion of the New Jersey coast. What term is applied to the wall-like structures that extend into the water? What is their purpose? In what direction are beach drift and longshore currents moving sand, toward the top of the photo or toward the bottom? 3. You and a friend set up an umbrella and chairs at a beach. Your friend then goes into the surf zone to play frisbee with another person. Several minutes later, your friend looks back toward the beach and is surprised to see that she is no longer near where the umbrella and chairs were set up. Although she is still in the surf zone, she is 30 yards away from where she started. How would you explain to your friend why she moved along the shore? 4. This surfer is enjoying a ride on a large wave along the coast of Maui. What was the source of energy that created this wave? B. How was the wavelength changing just prior to the time when this photo was taken? C. Why was the wavelength changing? D. Many ocean waves exhibit circular orbital motion. Is that true of the wave in this photo? Explain. 5. Assume that it is late September 2018, and Hurricane Gordon, a Category 5 storm, is projected to follow the path shown on the accompanying map. The path of the arrow represents the path of the hurricane's eye. Answer the following questions. A. Should the city of Houston expect to experience Gordon's fastest winds and greatest storm surge? Explain why or why not. B. What is the greatest threat to life and property if this storm approaches the Dallas-Fort Worth area? Explain your reasoning. 6. A friend wants to purchase a vacation home on a barrier island. If consulted, what advice would you give your friend? 7. Hurricane Rita was a major storm that struck the Gulf Coast in late September 2005, less than a month after Hurricane Katrina. The accompanying graph shows changes in air pressure and wind speed from the storms beginning as an unnamed tropical disturbance north of the Dominican Republic on September 18 until its last remnants faded away in Illinois on September 26. Use the graph to answer these questions. Which line represents air pressure, and which line represents wind speed? How did you figure this out? B. What was the storm's maximum wind speed, in knots? Convert this answer to kilometers per hour by multiplying by 1.85. C. What was the lowest pressure attained by Hurricane Rita? D. Using wind speed as your guide, what was the highest category reached on the Saffir-Simpson scale? On what day was this status reached? E. When landfall occurred, what was the category of Hurricane Rita? Figure 17.9 to 1 full alternative text description. 8. The force of gravity plays a critical role in creating ocean tides. The more massive an object, the stronger its gravitational pull. Explain why the sun's influence is only about half that of the moon, even though the sun is much more massive than the moon. 9. This photo shows a portion of the Maine coast. The brown muddy area in the foreground is influenced by tidal currents. What term is applied to this muddy area? Name the type of tidal current this area will experience in the hours to come. Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, in the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 18 Geologic Time. The Colorado River above Havasu Creek in Grand Canyon National Park. Millions of years of Earth history are exposed in the canyon's rock walls. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 18.1 Distinguish between numerical and relative dating and apply relative dating principles to determine a time sequence of geologic events. 18.2 Define fossil and discuss the conditions that favor the preservation of organisms as fossils. List and describe various types of fossils. 18.3 Explain how rocks of similar age that are in different places can be matched up. 18.4 Discuss 3 ways that atomic nuclei change and explain how unstable isotopes are used to determine numerical dates. 18.5 Explain how reliable numerical dates are determined for layers of sedimentary rock. 18.6 Distinguish among the 4 basic time units that make up the geologic time scale and explain why the time scale is considered to be a dynamic tool. In the late 18th century, James Hutton recognized the immensity of Earth history and the importance of time as a component in all geologic processes. In the 19th century, Sir Charles Lyell and others effectively demonstrated that Earth had experienced many episodes of mountain building and erosion, which must have required great spans of geologic time. Although these pioneering scientists understood that Earth was very old, they had no way of determining its age in years. Was it tens of millions, hundreds of millions, or even billions of years old? Long before geologists could establish a geologic calendar that included numerical dates in years, they gradually assembled a time scale using relative dating principles. What are these principles? What part do fossils play? With the discovery of radioactivity and radiometric dating techniques, geologists can now assign quite accurate dates to many of the events in Earth history. What is radioactivity? Why is it a good clock for dating the geologic past? 18.1 Creating a time scale, relative dating principles. Distinguish between numerical and relative dating and apply relative dating principles to determine a time sequence of geologic events. Figure 18.1 shows a hiker resting atop the Permian Age Kaibab Formation at Cape Royal on the north rim of the Grand Canyon. Beneath him are thousands of meters of sedimentary strata that go as far back as Cambrian time, more than 540 million years ago. These strata rest atop even older sedimentary, metamorphic, and igneous rocks from a span known as the Precambrian. Some of these rocks are 2 billion years old. Although the Grand Canyon's rock record has numerous interruptions, the rocks beneath the hiker contain clues to great spans of Earth history. Earth's long and complicated history is recorded in the structure, sequence, and properties of its rocks, sediments, and fossils. This hiker is resting atop the Kaibab Formation, the uppermost layer in the Grand Canyon. The importance of a time scale. Figure 18.1 Contemplating geologic time. Like the pages in a long and complicated history book, rocks record the geologic events and changing life forms of the past. The book, however, is not complete. Many pages, especially in the early chapters, are missing. Others are tattered, torn, or smudged. Yet enough of the book remains to allow much of the story to be deciphered. Interpreting Earth history is a prime goal of the science of geology. Like a modern-day sleuth, a geologist must interpret the clues found preserved in the rocks. By studying rocks, especially sedimentary rocks, and the features they contain, geologists can unravel the complexities of the past. Geologic events by themselves, however, have little meaning until they are put into a time perspective. Studying history, whether it is the Civil War or the age of dinosaurs, requires a calendar. Among geology's major contributions to human knowledge are the geologic time scale and the discovery that Earth history is exceedingly long. Numerical and relative dates. The geologists who developed the geologic time scale revolutionized the way people think about time and perceive our planet. They learned that Earth is much older than anyone had previously imagined and that its surface and interior have been changed over and over again by the same geologic processes that operate today. Numerical dates. During the late 1800s and early 1900s, attempts were made to determine Earth's age. Although some of the methods appeared promising at the time, none of those early efforts proved to be reliable. What those scientists were seeking was a numerical date. Such dates specify the actual number of years that have passed since an event occurred. Today, our understanding of radioactivity allows us to accurately determine numerical dates for rocks that represent important events in Earth's distant past. We will study radioactivity later in this chapter. Prior to the discovery of radioactivity, geologists had no reliable method of numerical dating and had to rely solely on relative dating. Relative dates. When we place rocks in their proper sequence of formation, indicating which formed first, second, third, and so on, we are establishing relative dates. Such dates cannot tell us how long ago something took place, only that it followed one event and preceded another. The relative dating techniques that were developed are valuable and still widely used. Numerical dating methods did not replace these techniques, they simply supplemented them. To establish a relative time scale, a few basic principles or rules had to be discovered and applied. They were major breakthroughs in thinking at the time, and their discovery was an important scientific achievement. Principle of superposition. Nicholas Steno, a Danish anatomist, geologist, and priest, was the first to recognize a sequence of historical events in an outcrop of sedimentary rock layers. Working in the mountains of western Italy, Steno applied a very simple rule that has become the most basic principle of relative dating, the principle of superposition. This principle simply states that in an undeformed sequence of sedimentary rocks, each bed is older than the one above and younger than the one below. Although it may seem obvious that a rock layer could not be deposited with nothing beneath it for support, it was not until 1669 that Steno clearly stated this principle. This rule also applies to other surface-deposited materials, such as lava flows and beds of ash from volcanic eruptions. Applying the principle of superposition to the beds exposed in the upper portion of the Grand Canyon, we can easily place the layers in their proper order. Among those that are pictured in Figure 18.2, the sedimentary rocks in the Supai group are the oldest, followed in order by the Hummoch Shale, Coconino Sandstone, Toroip Formation, and Kaibab Limestone. According to the principle of superposition, the Supai group is oldest of these layers in the upper portion of the Grand Canyon, and the Kaibab Limestone is youngest. Figure 18.2 Superposition. Figure 18.2 Full alternative text description. Principle of original horizontality. Steno is also credited with recognizing the importance of another basic rule, the principle of original horizontality, which states that layers of sediment are generally deposited in a horizontal position. Thus, if we observe rock layers that are flat, it means they have not been disturbed and still have their original horizontality. The layers in the Grand Canyon illustrate this in figures 18.1 and 18.2. But if they are folded or inclined at a steep angle, they must have been moved into that position by crustal disturbances sometime after their deposition. Most layers of sediment are deposited in a nearly horizontal position. When we see strata that are folded or tilted, we can assume that they were moved into that position by crustal disturbances after their deposition. Principle of lateral continuity. Figure 18.3 Original horizontality. The principle of lateral continuity refers to the fact that sedimentary beds originate as continuous layers that extend in all directions until they eventually grade into a different type of sediment or until they thin out at the edge of the basin of deposition. For example, when a river creates a canyon, we can assume that identical or similar strata on opposite sides once spanned the canyon. Although rock outcrops may be separated by a considerable distance, the principle of lateral continuity tells us that those outcrops once formed a continuous layer. This principle allows geologists to relate rocks in isolated outcrops to one another. Combining the principles of lateral continuity and superposition lets us extend relative age relationships over broad areas. This process, called correlation, is examined in section 18.3. Sediments are deposited over a large area in a continuous sheet. Sedimentary strata extend continuously in all directions until they thin out at the edge of a depositional basin or grade into a different type of sediment. Figure 18.4 Lateral continuity. Principle of cross-cutting relationships. Figure 18.5 shows a mass of rock that is offset by a fault, a fracture in rock along which displacement occurs. It is clear that the rocks must be older than the fault that broke them. The principle of cross-cutting relationship states that geologic features that cut across rocks must have formed after the rocks they cut through. Igneous intrusions provide another example. The dike shown in Figure 18.6 is a tabular mass of igneous rock that cuts through the surrounding rocks. The magmatic heat from igneous intrusions often creates a narrow, baked zone of contact metamorphism on the adjacent rock, also indicating that the intrusion occurred after the surrounding rocks were in place. The rocks are older than the fault that displaced them. Smart Figure 18.5 Cross-cutting fault. An igneous intrusion is younger than the rocks that are intruded. Watch Condor video, Principles of Relative Dating Figure 18.6 Cross-cutting dike. Principle of inclusions. Sometimes inclusions can aid in the relative dating process. Inclusions are fragments of one rock unit that have been enclosed within another. The principle of inclusions is logical and straightforward. The rock mass adjacent to the one containing the inclusions must have been there first in order to provide the rock fragments. Therefore, the rock mass that contains inclusions is the younger of the two. For example, when magma intrudes into surrounding rock, blocks of the surrounding rock may become dislodged and incorporated into the magma. If these pieces do not melt, they remain as inclusions, known as xenoliths. In another example, when sediment is deposited atop a weathered mass of bedrock, pieces of the weathered rock become incorporated into the younger sedimentary layer. The rock containing inclusions is younger than the inclusions. Smart Figure 18.7 Inclusions. Smart Figure 18.7 Full Alternative Text Description. Unconformities. When we observe layers of rock that have been deposited essentially without interruption, we call them conformable. Particular sites exhibit conformable beds representing certain spans of geologic time. However, no place on Earth has a complete set of conformable strata. Watch tutorial, Relative Dating. Throughout Earth history, the deposition of sediment has been interrupted over and over again. All such breaks in the rock record are termed unconformities. An unconformity represents a long period during which deposition ceased, erosion removed previously formed rocks, and then deposition resumed. In each case, uplift and erosion are followed by subsidence and renewed sedimentation. Unconformities are important features because they represent significant geologic events in Earth history. There are three basic types of unconformities, and their recognition helps geologists identify what intervals of time are not represented by strata and thus are missing from the geologic record. Angular unconformity. Perhaps the most easily recognized unconformity is an angular unconformity. It consists of tilted or folded sedimentary rocks that are overlain by younger, more flat-lying strata. An angular unconformity indicates that during a pause in deposition, a period of deformation and erosion occurred. An angular unconformity represents an extended period during which deformation and erosion occurred. Numbers on the diagram indicate the order in which events occurred. Smart Figure 18.8 Formation of an angular unconformity. Smart Figure 18.8 Full Alternative Text Description. When James Hutton studied an angular unconformity in Scotland more than 200 years ago, he understood that it represented a major episode of geologic activity. He and his colleagues also appreciated the immense time span implied by such relationships. When a companion later wrote of their visit to this site, he stated that the mind seemed to grow giddy by looking so far into the abyss of time. Watch tutorial, Unconformities. James Hutton studied this famous unconformity in the late 1700s. Disconformity. Figure 18.9 Siccar Point, Scotland. A disconformity is a gap in the rock record that represents a period during which erosion rather than deposition occurred. Imagine that a series of sedimentary layers is deposited in a shallow marine setting. Following this period of deposition, sea level falls or the land rises, exposing some of the sedimentary layers. During this span, when the sedimentary beds are above sea level, no new sediment accumulates, and some of the existing layers are eroded away. Later, sea level rises or the land subsides, submerging the landscape. Now the surface is again below sea level, and a new series of sedimentary beds is deposited. The boundary separating the two sets of beds is a disconformity, a span for which there is no rock record. Because the layers above and below a disconformity are parallel, these features are sometimes difficult to identify unless you notice evidence of erosion such as a buried stream channel. Did you know? Early attempts at determining Earth's age proved to be unreliable. One method reasoned that if the rate at which sediment accumulates could be determined, as well as the total thickness of sedimentary rock that had been deposited during Earth history, an estimate of Earth's age could be made. All that was necessary was to divide the rate of sediment accumulation into the total thickness of sedimentary rock. This method was riddled with difficulties. Can you think of some of them? The layers on both sides of this gap in the rock record are essentially parallel. Nonconformity. The third basic type of unconformity is a nonconformity, in which younger sedimentary strata overlie older metamorphic or intrusive igneous rocks. Just as angular unconformities and some disconformities imply crustal movements, so too do nonconformities. Intrusive igneous masses and metamorphic rocks originate far below the surface. Thus, for a nonconformity to develop, there must be a period of uplift and erosion of overlying rocks. Once exposed at the surface, the igneous or metamorphic rocks are subjected to weathering and erosion and then undergo subsidence and renewed sedimentation. Figure 18.10 Disconformity. Younger sedimentary rocks rest atop older metamorphic or igneous rocks. Figure 18.11 Full alternative text description. Unconformities in the Grand Canyon. The rocks exposed in the Grand Canyon of the Colorado River represent a tremendous span of geologic history. It is a wonderful place to take a trip through time. The canyon's colorful strata record a long history of sedimentation in a variety of environments, advancing seas, rivers and deltas, tidal flats and sand dunes. But the record is not continuous. Unconformities represent vast amounts of time that have not been recorded in the canyon's layers. Figure 18.12 is a geologic cross-section of the Grand Canyon. All three types of unconformities can be seen in the canyon walls. Figure 18.11 Nonconformity. All three types of unconformities are present. Figure 18.12 Full alternative text description. Applying relative dating principles. Figure 18.12 Cross-section of the Grand Canyon. If you apply the principles of relative dating to the hypothetical geologic cross-section in Figure 18.13, you can place in proper sequence the rocks and the events they represent. The statements within the figures summarize the logic used to interpret the cross-section. Smart Figure 18.13 Full alternative text description. Smart Figure 18.13 Applying principles of relative dating. Watch tutorial, Geologic Histories. In this example, we establish a relative time scale for the rocks and events in the area of the cross-section. Remember that this method gives us no idea how many years of Earth history are represented, for we have no numerical dates. Nor do we know how this area compares to any other. Concept checks 18.1. 1. Distinguish between numerical dates and relative dates. 2. Sketch and label 4 simple diagrams that illustrate each of the following: superposition, original horizontality, lateral continuity, and cross-cutting relationships. 3. What is the significance of an unconformity? 4. Distinguish among angular unconformity, disconformity, and nonconformity. This pioneering geologist is discussed in the section on the birth of modern geology in Chapter 1. 18.2 Fossils, evidence of past life. Define fossil and discuss the conditions that favor the preservation of organisms as fossils. List and describe various types of fossils. Did you know? The word fossil comes from the Latin fossilium, which means dug up from the ground. As originally used by medieval writers, a fossil was any stone, ore, or gem that came from an underground source. In fact, many early books on mineralogy are called books of fossils. The current meaning of fossil came about during the 1700s. Fossils, the remains or traces of prehistoric life, are important inclusions in sediment and sedimentary rocks. They are basic and important tools for interpreting the geologic past. The scientific study of fossils is called paleontology. It is an interdisciplinary science that blends geology and biology in an attempt to understand all aspects of the evolution of life over the vast expanse of geologic time. Knowing the nature of the life forms that existed at a particular time helps researchers understand past environmental conditions. Further, fossils are important time indicators and play a key role in correlating rocks of similar ages that are from different places. Types of fossils. Fossils are of many types. The remains of relatively recent organisms may not have been altered at all. Objects such as teeth, bones, and shells are common examples. Far less common are entire animals, flesh included, that have been preserved because of rather unusual circumstances. Remains of prehistoric elephants called mammoths that were frozen in the Arctic tundra of Siberia and Alaska are examples, as are the mummified remains of sloths preserved in a dry cave in Nevada. The fossils here are actual remains. Figure 18.14 La Brea tar pits. Permineralization. When mineral-rich groundwater permeates porous tissue such as bone or wood, minerals precipitate out of solution and fill pores and empty spaces, a process called permineralization. The formation of petrified wood involves permineralization with silica, often from a volcanic source such as a surrounding layer of volcanic ash. The wood is gradually transformed into chert, sometimes with colorful bands from impurities such as iron or carbon. The word petrified literally means turned into stone. Sometimes the microscopic details of the petrified structure are faithfully retained. Photo A by Bernhard Edmayer, science source. Photo B by E. J. Tarbuck. Photo C by Fluorescent Fossil Beds and National Monument. Photo D by E. J. Tarbuck. Photo E by Colin Keats Dorling Kindersley. Media Library. Photo F by E. J. Tarbuck. Figure 18.15 Full alternative text description. Molds and casts. Figure 18.15 Types of fossils. Another common class of fossils is molds and casts. When a shell or another structure is buried in sediment and then dissolved by underground water, a mold is created. The mold faithfully reflects the shape and surface marking of the organism, however, it does not reveal any information concerning its internal structure. If these hollow spaces are subsequently filled with mineral matter, casts are created. Carbonization and impressions. A type of fossilization called carbonization is particularly effective at preserving leaves and delicate animal forms. It occurs when fine sediment encases the remains of an organism. As time passes, pressure squeezes out the liquid and gaseous components and leaves behind a thin residue of carbon. Black shale deposited as organic-rich mud in oxygen-poor environments often contains abundant carbonized remains. If the film of carbon is lost from a fossil preserved in fine-grained sediment, a replica of the surface, called an impression, may still show considerable detail. Amber. Delicate organisms, such as insects, are difficult to preserve and consequently they are relatively rare in the fossil record. However, amber, the hardened resin of ancient trees, can preserve them in exquisite three-dimensional detail. The spider in figure 18.15e was preserved after being trapped in a drop of sticky resin. Resin sealed off the insect from the atmosphere and protected the remains from damage by water and air. As the resin hardened, a protective pressure-resistant case was formed. Trace fossils. In addition to the fossils already mentioned, there are numerous other types, many of them only traces of prehistoric life. Examples of such indirect evidence include tracks, animal footprints made in soft sediment that later turned into sedimentary rock. Burrows, tubes in sediment, wood, or rock made by an animal. These holes may later become filled with mineral matter and preserved. Some of the oldest known fossils are believed to be worm burrows. Coprolites, fossil dung and stomach contents that can provide useful information pertaining to the size and food habits of organisms. Gastroliths, highly polished stomach stones that were used in the grinding of food by some dinosaurs and other organisms. Did you know? People frequently confuse paleontology and archaeology. Paleontologists study fossils and are concerned with all life forms in the geologic past. By contrast, archaeologists focus on the material remains of past human life. These remains include both the objects used by people long ago, called artifacts, and the buildings and other structures associated with where people lived, called sites. Conditions favoring preservation. Only a tiny fraction of the organisms that have lived during the geologic past have been preserved as fossils. Normally, the remains of an animal or a plant are destroyed. Under what circumstances are they preserved? Two special conditions appear to be necessary: rapid burial and the possession of hard parts. When an organism perishes, its soft parts usually are quickly eaten by scavengers or decomposed by bacteria. Occasionally, however, the remains are buried by sediment. When this occurs, the remains are protected from the surface environment, where destructive processes operate. Rapid burial, therefore, is an important condition favoring preservation. In addition, animals and plants have a much better chance of being preserved as part of the fossil record if they have hard parts. Although traces and imprints of soft-bodied animals such as jellyfish, worms, and insects exist, they are not common. Flesh usually decays so rapidly that preservation is exceedingly unlikely. Hard parts such as shells, bones, and teeth predominate in the record of past life. Because preservation is contingent on special conditions, the record of life in the geologic past is biased. The fossil record of those organisms with hard parts that lived in areas of sedimentation is quite abundant. However, we get only an occasional glimpse of the vast array of other life forms that did not meet the special conditions favoring preservation. Concept checks 18.2. 1. Describes several ways that an animal or a plant can be preserved as a fossil. 2. List 3 examples of trace fossils. 3. What conditions favor the preservation of an organism as a fossil? 18.3 Correlation of rock layers. Explain how rocks of similar age that are in different places can be matched up. To develop a geologic time scale that is applicable to the entire Earth, rocks of similar age in different regions must be matched up. Such a task is called correlation. Correlating the rocks from one place to another makes possible a more comprehensive view of the geologic history of a region. Figure 18.16, for example, shows the correlation of strata at 3 sites on the Colorado Plateau in southern Utah and northern Arizona. No single locale exhibits the entire sequence, but correlation reveals a more complete picture of the sedimentary rock record. Matching strata at 3 locations on the Colorado Plateau. Figure 18.16 Correlation. Figure 18.16 Full alternative text description. Did you know? Even when organisms die and their tissues decay, the organic compounds of which they were made may survive in sediments. These are called chemical fossils. Commonly, these hydrocarbons form oil and gas, but some residues can persist in the rock record and can be analyzed to determine the kind of organisms from which they are derived. Correlation within limited areas. Within a limited area, geologists can correlate rocks of one locality with those of another by simply walking along the outcropping edges, but this may not be possible when the rocks are mostly concealed by soil and vegetation. Correlation over short distances is often achieved by noting the position of a bed in a sequence of strata. Or a layer may be identified in another location if it is composed of distinctive or uncommon minerals. However, when correlation between widely separated areas or between continents is the objective, geologists must rely on fossils. Fossils and correlation. The existence of fossils had been known for centuries, yet it was not until the late 1700s and early 1800s that their significance as geologic tools was made evident. During this period, an English engineer and canal builder, William Smith, discovered that each rock formation in the canals he worked on contained fossils unlike those in the beds either above or below. Further, he noted that sedimentary strata in widely separated areas could be identified and correlated based on their distinctive fossil content. Principle of fossil succession. Based on Smith's classic observations and the findings of many later geologists, one of the most important and basic principles in historical geology was formulated: fossil organisms succeed one another in a definite and determinable order, and therefore any time period can be recognized by its fossil content. This has come to be known as the principle of fossil succession. In other words, when fossils are arranged according to their age, they do not present a random or haphazard picture. To the contrary, fossils document the evolution of life through time. For example, an age of trilobites is recognized quite early in the fossil record. Then, in succession, paleontologists recognize an age of fishes, an age of coal swamps, an age of reptiles, and an age of mammals. These ages pertain to groups that were especially plentiful and characteristic during particular time periods. Within each of the ages are many subdivisions, based, for example, on certain species of trilobites and certain types of fish, reptiles, and so on. This same succession of dominant organisms, never out of order, is found on every continent. Index fossils and fossil assemblages. When fossils were found to be time indicators, they became the most useful means of correlating rocks of similar age in different regions. Geologists pay particular attention to certain fossils called index fossils. These fossils are widespread geographically but limited to a short span of geologic time, so their presence provides an important method of matching rocks of the same age. Rock formations, however, do not always contain a specific index fossil. In such situations, a group of fossils, called a fossil assemblage, is used to establish the age of the bed. Figure 18.18 illustrates how an assemblage of fossils may be used to date rocks more precisely than could be accomplished by the use of any single fossil. Since microfossils are often very abundant, widespread, and quick to appear and become extinct, they constitute ideal index fossils. This scanning electron micrograph shows marine microfossils from the Miocene epoch. Figure 18.17 Index fossils. Overlapping ranges of fossils help date rocks more exactly than using a single fossil. Smart Figure 18.18 Full alternative text description. Smart Figure 18.18 Fossil assemblage. Watch tutorial. Fossil ranges. Environmental indicators. In addition to being important, and often essential, tools for correlation, fossils are important environmental indicators. Although we can deduce much about past environments by studying the nature and characteristics of sedimentary rocks, a close examination of the fossils present can usually provide a great deal more information. For example, when the remains of certain clam shells are found in limestone, a geologist quite reasonably assumes that the region was once covered by a shallow sea. Fossils can also at times be used to identify the approximate position of an ancient shoreline. Given what we know of living organisms, we can conclude that fossil animals with thick shells, capable of withstanding pounding and surging waves, inhabited shorelines. On the other hand, animals with thin, delicate shells probably indicate deep, calm offshore waters. Fossils also can be used to indicate the former temperature of the water. Certain kinds of present-day corals must live in warm and shallow tropical seas like those around Florida and the Bahamas. When similar types of coral are found in ancient limestones, they indicate the marine environment that must have existed when they were alive. These examples illustrate how fossils can help unravel the complex story of Earth history. Concept checks 18.3. 1. What is the goal of correlation? 2. State the principle of fossil succession in your own words. 3. Contrast index fossil and fossil assemblage. 4. Along with their value for correlation, how else are fossils useful to geologists? 18.4 Numerical dating with nuclear decay. Discuss 3 ways that atomic nuclei change and explain how unstable isotopes are used to determine numerical dates. In addition to establishing relative dates by using the principles described in the preceding sections, scientists can also obtain reliable numerical dates for events in the geologic past. For example, we know that Earth is about 4.6 billion years old and that the dinosaurs became extinct about 66 million years ago. Dates that are expressed in millions and billions of years truly stretch our imagination because our personal calendars involve time measured in hours, weeks, and years. In this section you will learn about radioactivity and its application in radiometric dating. Our understanding of changes in the nuclei of atoms has allowed us to determine that geologic time is vast. This immense span is often referred to as deep time. Radiometric dating allows us to measure it quantitatively. Reviewing basic atomic structure. Recall from Chapter 3 that each atom has a nucleus that contains protons and neutrons and that the nucleus is orbited by electrons. Electrons have a negative electrical charge, and protons have a positive charge. A neutron has no charge, but it can be converted to a positively charged proton plus a negatively charged electron. The atomic number is the number of protons in the nucleus. Every element has a different number of protons and thus a different identifying atomic number. Atoms of the same element always have the same number of protons, so the atomic number stays constant. Practically all of an atom's mass is in the nucleus, indicating that electrons have virtually no mass at all. So, by adding the protons and neutrons in an atom's nucleus, we derive the atom's mass number. The number of neutrons can vary, and these variants, or isotopes, have different mass numbers. To summarize with an example, uranium's nucleus always has 92 protons, so its atomic number is always 92. But its neutron population varies, so uranium has 3 isotopes: uranium-234, uranium-235, and uranium-238. All 3 isotopes are mixed in nature. They look the same and behave the same in chemical reactions. Changes to atomic nuclei. Usually, the forces that stabilize atomic nuclei are strong. However, in some isotopes, the forces that bind protons and neutrons are not strong enough to keep them together forever. Such nuclei are unstable and spontaneously break apart in a process called nuclear decay. As time goes by, more and more of the unstable atoms decay, producing an ever-growing number of stable isotopes. Not all isotopes are unstable, there are stable isotopes, too, but here we focus on the unstable isotopes and the stable isotopes they produce. What happens when unstable atoms break apart? 3 common types of nuclear decay are illustrated in Figure 18.19. Alpha particles may be emitted from the nucleus. An alpha particle is composed of 2 protons and 2 neutrons. Thus, the emission of an alpha particle means that the mass number of the isotope is reduced by 4, and the atomic number is lowered by 2. When an electron is emitted from a nucleus, the mass number remains unchanged because electrons have practically no mass. However, the electron is produced when a neutron decays to produce the electron plus a proton. Because the nucleus now contains 1 more proton than before, the atomic number increases by 1. It's no longer the same element. Sometimes an electron is captured by the nucleus. The electron combines with a proton and forms an additional neutron. As in the last example, the mass number remains unchanged. However, because the nucleus now contains 1 fewer proton, the atomic number decreases by 1. Notice that in each example, the number of protons in the nucleus changes, thus producing a different element. Figure 18.19 Full alternative text description. Figure 18.19 Changing atomic nuclei. An unstable isotope is referred to as the parent, and the isotopes resulting from the decay of the parent are termed the daughter products. But the path from parent to daughter isn't always direct. Uranium-238, one of the most important isotopes for geologic dating, provides an example of the complexity. When the radioactive parent, uranium-238 decays, it follows a number of steps, emitting a total of 8 alpha particles and 6 electrons before finally becoming the stable daughter product lead-206. Uranium-238 is an example of a nuclear decay series. Before the stable end product is reached, many different isotopes are produced as intermediate steps. Figure 18.20 Decay of U-238. Figure 18.20 Full alternative text description. Radiometric dating. Nuclear decay provides a reliable way of calculating the ages of rocks and minerals that contain particular unstable isotopes. The procedure is called radiometric dating. Radiometric dating is reliable because the rates of decay for many isotopes have been precisely measured and do not vary under the physical conditions that exist in Earth's outer layers. Therefore, each unstable isotope used for dating has been decaying at a fixed rate since the formation of the mineral crystals in which we find it, and the products of its decay have been accumulating in that crystal at a corresponding rate. For example, some minerals are able to incorporate uranium atoms in their crystal lattice. When such a mineral crystallizes from magma, it contains no lead from previous decay. The radiometric clock starts at this point. As the uranium in this newly formed mineral decays, atoms of the daughter product accumulate, trapped in the crystal, and eventually build up to measurable levels. Similarly, when a crystal of feldspar forms, some of the potassium atoms incorporated into its lattice will be the unstable isotope potassium-40. These atoms will decay at a steady rate by electron capture to produce the daughter argon-40. Over time, there is less and less of the parent potassium and more of the daughter argon. Half-life. The time required for half of the nuclei in a sample of a given unstable isotope to decay is called the half-life of that isotope. Half-life is a common way of expressing the rate of radioactive decay. Figure 18. 21 illustrates what occurs when a radioactive parent decays directly into its stable daughter product. When the quantities of parent and daughter are equal, we know that one half-life has transpired. When 1/4 of the original parent atoms remain and 3/4 have decayed to the daughter product, the parent-daughter ratio is 1:3, and we know that 2 half-lives have passed. After 3 half-lives, the ratio of parent atoms to daughter atoms is 1:7. Change is exponential. Half of the unstable parent atoms remain after 1 half-life. After a second half-life, 1/4 of the parent atoms remain, and so forth. Smart Figure 18.21 Changing Parent-Daughter Ratios. Smart Figure 18.21 Full alternative text description. Watch tutorial, half-life. If the half-life of a radioactive isotope is known and the parent-daughter ratio can be determined, the age of the sample can be calculated. For example, assume that the half-life of a hypothetical unstable isotope is 1 million years, and the parent-daughter ratio in a sample is 1:15. This ratio indicates that 4 half-lives have passed and that the sample must be 4 million years old. Notice that the percentage of radioactive atoms that decay during one half-life is always the same, 50%. However, the actual number of atoms that decay with the passing of each half-life continually decreases. Thus, as the percentage of radioactive parent atoms declines, the proportion of stable daughter atoms rises, with the increase in daughter atoms just matching the drop in parent atoms. This fact is the key to radiometric dating. Using unstable isotopes. Of the many radioactive isotopes that exist in nature, 5 have proved particularly useful in providing radiometric ages for ancient rocks. Rubidium-87, thorium-232, and the 2 listed isotopes of uranium are used only for dating rocks that are millions of years old, but potassium-40 is more versatile. Although the half-life of potassium-40 is 1.3 billion years, analytical techniques make it possible to detect tiny amounts of its stable daughter product, argon-40, in some rocks that are younger than 100,000 years. Another important reason for its frequent use is that potassium is an abundant constituent of many common minerals, particularly micas and feldspars. Table 18.1 Full alternative text description. Table 18.1 Isotopes frequently used in radiometric dating. A complex process. Although the basic principle of radiometric dating is simple, the actual procedure is quite complex. The chemical analysis that determines the quantities of parent and daughter must be painstakingly precise. In addition, some radioactive materials do not decay directly into the stable daughter product, and this fact may further complicate the analysis. In the case of uranium-238, there are 13 intermediate unstable daughter products formed before the 14th and last daughter product, the stable isotope Lead-206, is produced. Sources of error. It is important to understand that an accurate radiometric date can be obtained only if there has been no leakage of parent or daughter isotopes between the mineral crystal and its surroundings in the time since the mineral formed. This is not always the case. In fact, a limitation of the potassium-argon method arises from the fact that argon is a gas, and it may leak from minerals, resulting in a radiometric age that is lower than the actual age. Indeed, losses can be significant if the rock is subjected to high temperatures. If the rock is heated to the point where all of the argon in its minerals escapes, then its radiometric clock will be reset, and radiometric dating will give the time of thermal resetting, not the true age of the rock. For other radiometric clocks, a loss of daughter atoms can occur if the rock has been subjected to weathering or leaching. To avoid such a problem, one simple safeguard is to use only fresh, unweathered material and not samples that exhibit signs of chemical alteration. To guard against error in radiometric dating, scientists often use cross-checks, subjecting a sample to two different methods. If the results agree, the likelihood is high that the date is reliable. If the results are appreciably different, other cross-checks must be employed to determine which, if either, is correct. Did you know? Although movies and cartoons have depicted humans and dinosaurs living side by side, this was never the case. Dinosaurs flourished during the Mesozoic era and became extinct about 65 million years ago. Humans and their close ancestors did not appear on the scene until the late Cenozoic, more than 60 million years after the demise of dinosaurs. Earth's oldest rocks. Radiometric dating has produced literally thousands of dates for events in Earth history. Rocks exceeding 3.5 billion years in age are found on all of the continents. Earth's oldest rocks may be as old as 4.28 billion years. Discovered in northern Quebec, Canada, on the shores of Hudson Bay, these rocks may be remnants of Earth's earliest crust. Rocks from western Greenland have been dated at 3.7 to 3.8 BY, and rocks nearly as old are found in the Minnesota River Valley and northern Michigan. 3. 5 to 3.7 BY, in southern Africa, and in Western Australia. Tiny crystals of the mineral zircon having radiometric ages as old as 4.3 BY have been found in younger sedimentary rocks in Western Australia. The source rocks for these tiny durable grains either no longer exist or have not yet been found. Radiometric dating has vindicated the ideas of Hutton, Darwin, and others, who more than 150 years ago inferred that geologic time must be immense. Indeed, modern dating methods have proved that there has been enough time for the processes we observe to have accomplished tremendous tasks. Dating with carbon-14. To date relatively recent events, carbon-14 is used. Carbon-14 is the radioactive isotope of carbon. The process is often called radiocarbon dating. Because the half-life of carbon-14 is only 5,730 years, radiocarbon dating can be used for dating events from the historic past as well as those from very recent geologic history. In some cases, carbon-14 can be used to date events as far back as 70,000 years. Carbon-14. 14C is continuously produced in the upper atmosphere as a result of cosmic ray bombardment. Cosmic rays shatter the nuclei of gas atoms, releasing neutrons. Some of the neutrons are absorbed by nitrogen atoms, causing each nucleus to emit a proton. As a result, the atomic number decreases by 1, and a different element, carbon-14, is created. This isotope of carbon quickly becomes incorporated into carbon dioxide, which circulates in the atmosphere and is absorbed by living matter. As a result, all organisms, including you, contain a small amount of carbon-14. You top off your 14 sea levels every time you eat something. Figure 18.22 Carbon-14. Production and decay of radiocarbon. These sketches represent the nuclei of the respective atoms. Figure 18.22 Full alternative text description. As long as an organism is alive, the decaying radiocarbon is continually replaced, and the proportions of carbon-14 and carbon-12 remain constant. Carbon-12 is the stable and most common isotope of carbon. However, when any plant or animal dies, the amount of carbon-14 gradually decreases as it decays to nitrogen-14 by beta emission. By comparing the proportions of carbon-14 and carbon-12 in a sample, radiocarbon dates can be determined. It is important to emphasize that carbon-14 can only be used to date organic materials, such as wood, charcoal, bones, flesh, and cloth. Although carbon-14 is only useful in dating the last small fraction of geologic time, it is a valuable tool for anthropologists, archaeologists, and historians, as well as for geologists who study very recent Earth history. In fact, the development of radiocarbon dating was considered so important that the chemist who discovered this application, Willard F. Libby, received a Nobel Prize in 1960. Chauvet Cave in southern France, discovered in 1994, contains some of the earliest known cave paintings. Radiocarbon dating indicates that most of the images were drawn between 30,000 and 32,000 years ago. Figure 18.23 Cave art. Did you know? Dating with carbon-14 is useful to archaeologists and historians as well as geologists. For example, University of Arizona researchers used carbon-14 dating to determine the age of the Dead Sea Scrolls, considered to be some of the greatest archaeological discoveries of the 20th century. Parchment from the scrolls dates between 150 and 5. Portions of the scrolls contain dates that match those determined by the carbon-14 measurements. Concept checks 18.4. 1. List 4 ways that unstable nuclei change. For each type, describe how the atomic number and atomic mass change. 2. Sketch a simple diagram that explains the idea of half-life. 3. Why is radiometric dating a reliable method for determining numerical dates? 4. For what time span does radiocarbon dating apply? 18.5 Determining numerical dates. For sedimentary strata. Explain how reliable numerical dates are determined for layers of sedimentary rock. Although reasonably accurate numerical dates have been worked out for the periods of the geologic time scale, the task is not without difficulty. The primary difficulty in assigning numerical dates to units of time is that not all rocks can be dated by using radiometric methods. For a radiometric date to be useful, all the minerals in the rock must have formed at about the same time. For this reason, unstable isotopes can be used to determine when minerals in an igneous rock crystallized and when pressure and heat created new minerals in a metamorphic rock. However, samples of sedimentary rock can only rarely be dated directly by radiometric means. Although a detrital sedimentary rock may include particles that contain unstable isotopes, the rock's age cannot be accurately determined because the grains composing the rock are not the same age as the rock in which they occur. Rather, the sediments have been weathered from rocks of diverse ages. Radiometric dates obtained from metamorphic rocks may also be difficult to interpret because the age of a particular mineral in a metamorphic rock does not necessarily represent the time when the rock initially formed. Instead, the date might indicate any one of a number of subsequent metamorphic phases. If samples of sedimentary rocks rarely yield reliable radiometric ages, how can numerical dates be assigned to sedimentary layers? Usually geologists must relate the strata to datable igneous masses, as in Figure 18.24. In this example, radiometric dating has determined the ages of the volcanic ash bed in the Morrison Formation and the dike cutting the Mancos Shale and Mesa Verde Formation. The sedimentary beds below the ash are obviously older than the ash, and all the layers above the ash are younger. The dike is younger than the Mancos Shale and the Mesa Verde Formation but older than the Wasatch Formation because the dike does not intrude this topmost layer. Figure 18.24 Dating sedimentary strata. Numerical dates for sedimentary layers are usually determined by examining their relationship to igneous rocks. Figure 18.24 Full alternative text description. From this kind of evidence, geologists estimate that the Morrison Formation was deposited more than 160 million years ago, as indicated by the ash bed. Further, they conclude that deposition of the Wasatch Formation began after the intrusion of the dike, 66 million years ago. This is one example of literally thousands that illustrate how datable materials are used to bracket the various episodes in Earth history within specific time periods. It shows the necessity of combining laboratory dating methods with field observations of rocks. Concept checks 18.5. 1. Briefly explain why it is often difficult to assign a reliable numerical date to a sample of sedimentary rock. 2. How might a numerical date for a layer of sedimentary rock be determined? 18.6 The geologic time scale. Distinguish among the four basic time units that make up the geologic time scale and explain why the time scale is considered to be a dynamic tool. Geologists have divided the whole of geologic history into units of varying length. Together, they compose the geologic time scale of Earth history. The major units of the time scale were delineated during the 19th century, principally by scientists in Western Europe and Great Britain. Because radiometric dating was unavailable at that time, the entire time scale was created using methods of relative dating. It was only in the 20th century that radiometric methods permitted numerical dates to be added. Figure 18.25 Geologic time scale, a basic reference. The time scale divides the vast 4.6 billion year history of Earth into eons, eras, periods, and epochs. Numbers on the time scale represent time in millions of years before the present. The Precambrian accounts for more than 88% of geologic time. Numerical dates were added long after the time scale was established using relative dating techniques. The dates appearing on this time scale are those currently accepted by the International Commission on Stratigraphy in 2015. The color scheme used on this chart was selected because it is similar to that used by the ICS. Figure 18.25 Full alternative text description. Structure of the time scale. The geologic time scale subdivides the 4.6 billion year history of Earth into many different units and provides a meaningful time frame within which the events of the geologic past are arranged. As shown in Figure 18.25, eons represent the greatest expanses of time. The eon that began about 542 million years ago is the Phanerozoic, a term derived from Greek words meaning visible life. It is an appropriate description because the rocks and deposits of the Phanerozoic eon contain abundant fossils that document major evolutionary trends. Another glance at the time scale reveals that eons are divided into eras. The Phanerozoic eon consists of the Paleozoic era, the Mesozoic era, and the Cenozoic era. As the names imply, these eras are bounded by profound worldwide changes in life forms. Each era of the Phanerozoic eon is further divided into time units known as periods. The Paleozoic has 7, and the Mesozoic and Cenozoic each have 3. Each of these periods is characterized by a somewhat less profound change in life forms compared with the eras. Each of the periods is divided into still smaller units called epochs. As you can see in Figure 18.25, 7 epochs have been named for the periods of the Cenozoic. The epochs of other periods usually are simply termed early, middle, and late. Precambrian time. Notice that the geologic time scale is considerably less detailed prior to the beginning of the Cambrian period, 541 million years ago. The nearly 4 billion years that precede the Cambrian are divided into two eons, the Archean and the Proterozoic. It is also common for this vast expanse of time to simply be referred to as the Precambrian. Why is the huge expanse of Precambrian time, which represents about 88% of Earth history, not divided into numerous eras, periods, and epochs? The reason is that Precambrian history is not known in great enough detail. In geology, as in human history, the farther back we go, the less we know. We know much more about the past decade than about the first century. Equally, in Earth history, the more recent past has the freshest, least disturbed, and most observable record. The further back in time a geologist goes, the more fragmented the record and clues become. There are also other reasons to explain our lack of a detailed time scale for this vast segment of Earth history. The first abundant fossil evidence does not appear in the geologic record until the beginning of the Cambrian period. Prior to the Cambrian, simple life forms such as algae, bacteria, fungi, and worms predominated. All of these organisms lack hard parts, an important condition favoring preservation. For this reason, there is only a meager Precambrian fossil record. Many exposures of Precambrian rocks have been studied in some detail, but correlation is often difficult when fossils are lacking. Because Precambrian rocks are very old, most have been subjected to a great many changes. Much of the Precambrian rock record is composed of highly distorted metamorphic rocks. This makes the interpretation of past environments difficult because many of the clues present in the original sedimentary rocks have been destroyed. Radiometric dating has provided a partial solution to the troublesome task of dating and correlating Precambrian rocks. But untangling the complex Precambrian record still remains a daunting task. Terminology and the geologic time scale. Some terms are associated with the geologic time scale but are not officially recognized as being a part of it. The best known, and most common, example is Precambrian, the informal name for the eons that came before the current Phanerozoic eon. Although the term Precambrian has no formal status on the geologic time scale, it has been traditionally used as though it does. Hadean is another informal term that is found on some versions of the geologic time scale and is used by many geologists. It refers to the earliest interval of Earth history, before the oldest known rocks. When the term was coined in 1972, the age of Earth's oldest known rocks was about 3.8 billion years. Today that number stands at slightly greater than 4 billion and, of course, is subject to revision. The name Hadean derives from Hades, Greek for underworld, a reference to the hellish conditions that prevailed on Earth early in its history. Effective communication in the geosciences requires that the geologic time scale consist of standardized divisions and dates. So, who determines which names and dates on the geologic time scale are official? The organization that is largely responsible for maintaining and updating this important document is the International Commission on Stratigraphy, a committee of the International Union of Geological Sciences. Advances in the geosciences require that the scale be periodically updated to include changes in unit names and boundary age estimates. For example, the geologic time scale shown in Figure 18.25 was updated in 2015. After considerable dialogue among geologists who focus on very recent Earth history, the ICS changed the date for the start of the Quaternary period and the Pleistocene epoch from 1.8 million to 2.6 million years ago. Perhaps by the time you read this, other changes will have been made. If you were to examine a geologic time scale from just a few years ago, it is quite possible that you would see the Cenozoic era divided into the Tertiary and Quaternary periods. However, on more recent versions, the space formerly designated as Tertiary is divided into the Paleogene and Neogene periods. As our understanding of this time span has changed, so too has its designation on the geologic time scale. Today, the Tertiary period is considered a historic name and is given no official status on the ICS version of the time scale. Many time scales still contain references to the Tertiary period, though, including figure 18.25. One reason for this is that a great deal of past geologic literature uses this name. Did you know? Some scientists have suggested that the Holocene epoch has ended and that we have entered a new epoch called the Anthropocene. It is considered to be the span in which the global environmental effects of increased human population and economic development have dramatically transformed Earth's surface. Although this term is used currently as an informal metaphor for human-caused global environmental change, a number of scientists feel that there is merit in recognizing the Anthropocene as a new, official, geologic epoch. For those who study historical geology, it is important to realize that the geologic time scale is a dynamic tool that continues to be refined as our knowledge and understanding of Earth history evolve. Concept checks 18.6. 1. List the 4 basic units that make up the geologic time scale. 2. Why is Zoic part of so many names on the geologic time scale? 3. What term applies to all of geologic time prior to the Phanerozoic Eon? Why is this span not divided into as many smaller time units as the Phanerozoic Eon? 4. To what does the term Hadean apply? Is it an official part of the geologic time scale? Major changes in life forms are discussed in Chapter 19. Concepts in review, geologic time. 18.1 Creating a time scale, relative dating principles. Distinguish between numerical and relative dating and apply relative dating principles to determine a time sequence of geologic events. Key terms. Numerical date, relative date. Principle of superposition, principle of original horizontality, principle of lateral continuity, principle of cross-cutting relationships, principle of inclusions, conformable unconformity. Angular unconformity, disconformity, nonconformity. The 2 types of dates that geologists use to interpret Earth history are relative dates, which put events in their proper sequence of formation, and numerical dates, which pinpoint the time in years when an event took place. Relative dates can be established using the principles of superposition, original horizontality, cross-cutting relationships, and inclusions. Unconformities, gaps in the geologic record, may be identified during the relative dating process. The accompanying photo shows 4 features. Place the features in the proper sequence, from oldest to youngest. Explain your reasoning. 18.2 Fossils, evidence of past life. Define fossil and discuss the conditions that favor the preservation of organisms as fossils. List and describe various types of fossils. Key terms. Fossil paleontology. Fossils are remains or traces of ancient life. Paleontology is the branch of science that studies fossils. Fossils can form through many processes. For an organism to be preserved as a fossil, it usually needs to be buried rapidly. Also, an organism's hard parts are most likely to be preserved because soft tissue decomposes rapidly in most circumstances. What term is used to describe the type of fossil that is shown here? Briefly describe how it formed. 18.3 Correlation of rock layers. Explain how rocks of similar age that are in different places can be matched up. Key terms. Correlation. Principle of fossil succession index, fossil assemblage. Matching up exposures of rock that are the same age but are in different places is called correlation. By correlating rocks from around the world, geologists developed the geologic time scale and obtained a fuller perspective on Earth history. Fossils can be used to correlate sedimentary rocks in widely separated places by using the rock's distinctive fossil content and applying the principle of fossil succession. The principle states that fossil organisms succeed one another in a definite and determinable order, and, therefore, a time period can be recognized by examining its fossil content. Index fossils are particularly useful in correlation because they are widespread and associated with a relatively narrow time span. The overlapping ranges of fossils in an assemblage may be used to establish an age for a rock layer that contains multiple fossils. Fossils may be used to establish ancient environmental conditions that existed when sediment was deposited. 18.4 Numerical dating with nuclear decay. Discuss 3 ways that atomic nuclei change and explain how unstable isotopes are used to determine numerical dates. Key terms: nuclear decay, radioactive decay, radiometric dating, half-life. Radiocarbon dating. Nuclear decay is the spontaneous breaking apart of certain unstable atomic nuclei. 3 common forms of nuclear decay are emission of an alpha particle from the nucleus, emission of a beta particle from the nucleus, and capture of an electron by the nucleus. Radiometric dating refers to the procedure by which unstable isotopes are used to determine numerical ages of rocks and minerals. It is reliable because the rates of decay for the isotopes that are used have been precisely measured and do not vary. The length of time it takes for 1/2 of the nuclei of an unstable parent isotope to change into its stable daughter product is called the half-life of that isotope. If the half-life is known, and the parent-daughter ratio can be measured, the age of the sample can be calculated. Measurements of zircon crystals containing trace amounts of uranium from a specimen of granite yield parent-daughter ratios of 25% parent and 75% daughter. The half-life of uranium-235 is 704 million years. How old is the granite? 18.5 Determining numerical dates for sedimentary strata. Explain how reliable numerical dates are determined for layers of sedimentary rock. Sedimentary strata are usually not directly datable using radiometric techniques because they consist of the material produced by the weathering of other rocks. A particle in a sedimentary rock comes from some older source rock. If you were to date the particle using unstable isotopes, you would get the age of the source rock, not the age of the sedimentary rock. One way geologists assign numerical dates to sedimentary rocks is to use relative dating principles to relate them to datable igneous masses, such as dikes and volcanic ash beds. A layer may be older than one igneous feature and younger than another. Express the numerical age of the sandstone layer in the diagram as accurately as possible. 18.6 The geologic time scale. Distinguish among the 4 basic time units that make up the geologic time scale and explain why the time scale is considered to be a dynamic tool. Key terms: geologic time scale, Eon. Phanerozoic Eon era, Paleozoic era, Mesozoic era. Cenozoic era, period, epoch, Archean, Proterozoic, Precambrian. Earth history is divided into units of time on the geologic time scale. Eons are divided into eras, which each contain multiple periods. Periods are divided into epochs. Precambrian time includes the Archean and Proterozoic eons. It is followed by the Phanerozoic eon, which is well documented by abundant fossil evidence, resulting in many subdivisions. The geologic time scale is a work in progress, continually being refined as new information becomes available. Is the Mesozoic an example of an eon, an era, a period, or an epoch? What about the Jurassic? Give it some thought. 1. The accompanying image shows the metamorphic rock gneiss, a basaltic dike, and a fault. Place these 3 features in their proper sequence and explain your logic. 2. A mass of granite is in contact with a layer of sandstone. Using a principle described in this chapter, explain how you might determine whether the sandstone was deposited on top of the granite or whether the magma that formed the granite was intruded after the sandstone was deposited. 3. This scenic image is from Monument Valley in the northeastern corner of Arizona. The bedrock in this region consists of layers of sedimentary rocks. Although the prominent rock exposures in this photo are widely separated, we can infer that they represent a once continuous layer. Discuss the principle that allows us to make this inference. 4. The accompanying photo shows 2 layers of sedimentary rock. The lower layer is shale from the late Mesozoic era. Note the old river channel that was carved into the shale after it was deposited. Above is a younger layer of boulder-rich breccia. Are these layers conformable? Explain why or why not. What term from relative dating applies to the line separating the two layers? 5. These polished stones are called gastroliths. Explain how such objects can be considered fossils. What category of fossil are they? Name another example of a fossil in this category. 6. If an unstable isotope of thorium emits 6 alpha particles and 4 beta particles during the course of radioactive decay, what are the atomic number and mass number of the stable daughter product? 7. A hypothetical unstable isotope has a half-life of 10,000 years. If the ratio of radioactive parent to stable daughter product is 1 to 3, how old is the rock that contains the radioactive material? 8. Solve the problems below that relate to the magnitude of Earth history. To make calculations easier, round Earth's age to 5 billion years. What percentage of geologic time is represented by recorded history? B. Human-like ancestors have been around for roughly 5 million years. What percentage of geologic time is represented by these ancestors? C. The first abundant fossil evidence for multicellular organisms does not appear until the beginning of the Cambrian period, about 540 million years ago. What percentage of geologic time is represented by this abundant fossil evidence? 9. A portion of a popular college text in historical geology includes 10 chapters in a unit titled The Story of Earth. 2 chapters are devoted to Precambrian time. By contrast, the last 2 chapters focus on the most recent 23 million years, with 25 of those pages devoted to the Holocene epoch, which began 10,000 years ago. A. Compare the percentage of pages devoted to the Precambrian to the percentage of geologic time that this span represents. B. How does the number of pages about the Holocene compare to its percentage of geologic time? C. Suggest some reasons the text seems to have such an unequal treatment of Earth history. 10. This scene in Montana's Glacier National Park shows layers of Precambrian sedimentary rocks. The darker layer contained within the sedimentary layers is igneous. The narrow, light-colored areas adjacent to the igneous rock were created when molten material that formed the igneous rock baked the adjacent rock. A. Is the igneous layer more likely a lava flow that was laid down at the surface prior to the deposition of the layers above it, or a sill that was intruded after all the sedimentary layers were deposited? Explain. B. Is it likely that the igneous layer will exhibit a vesicular texture? Explain. C. To which group does the light-colored rock belong? Relate your explanation to the rock cycle. 11. The accompanying diagram is a cross-section of a hypothetical area. Place the lettered features in the proper sequence from oldest to youngest. Where in the sequence can you identify an unconformity? Figure 18.8 to 1 full alternative text description. 12. This is a close-up view of the detrital sedimentary rock conglomerate. Assume that this rock contains radioactive isotopes that will yield numerical dates. A. Although radioactive isotopes are present, a reliable numerical date for this conglomerate cannot be accurately determined. Explain. B. How might a numerical age range be established for the conglomerate layer? Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, in the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 19: Earth's Evolution Through Geologic Time. The Grand Prismatic Pool in Yellowstone National Park is a hot water pool that gets its blue color from several species of heat-tolerant cyanobacteria. Microscopic fossils of organisms similar to modern cyanobacteria are among Earth's oldest fossils. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 19.1 List the principal characteristics that make Earth unique among the planets in the solar system. 19.2 Outline the major stages in Earth's evolution, from the Big Bang to the formation of our planet's layered internal structure. 19.3 Describe how Earth's atmosphere and oceans formed and evolved through time. 19.4 Explain the formation of continental crust, how continental crust becomes assembled into continents, and the role that the supercontinent cycle has played in this process. 19.5 List and discuss the major geologic events in the Paleozoic, Mesozoic, and Cenozoic eras. 19.6 Describe some of the hypotheses on the origin of life and the characteristics of early prokaryotes, eukaryotes, and multicellular organisms. 19.7 List the major developments in the history of life during the Paleozoic era. 19.8 Briefly explain the major developments in the history of life during the Mesozoic era. 19.9 Discuss the major developments in the history of life during the Cenozoic era. Earth has a long and complex history. Time and again, the splitting and colliding of continents has led to the formation of new ocean basins and the creation of great mountain ranges. Furthermore, the nature of life on our planet has undergone dramatic changes through time. 19.1 Is Earth unique? List the principal characteristics that make Earth unique among the planets in the solar system. Although we have now sent spacecraft to every planet in our solar system and have identified several thousand planets that orbit other stars, we know of only one place that supports life, our own modest-sized planet Earth. Life on Earth is ubiquitous. It is found in boiling mudpots and hot springs, in the deep abyss of the ocean, and even under the Antarctic ice sheet. Living space on our planet, however, is significantly limited when we consider the needs of individual organisms, particularly humans. The global ocean covers 71% of Earth's surface, but only a few hundred meters below the water's surface. Pressures are so intense that humans cannot survive without an atmospheric diving suit or submersible. In addition, many continental areas are too steep, too high, or too cold for us to inhabit. Figure 19.1 Climbers near the top of Mount Everest. Much of Earth's surface is uninhabitable by humans. At this altitude, the level of oxygen is only one-third the amount available at sea level. What fortuitous events produced a planet so hospitable to life? Earth was not always as we find it today. During its formative years, our planet became hot enough to support a magma ocean. It also survived a several hundred million-year period of extreme bombardment by asteroids, to which the heavily cratered surfaces of Mars and the Moon testify. The oxygen-rich atmosphere that makes higher life forms possible developed relatively recently. Serendipitously, Earth seems to be the right planet, in the right location, at the right time. The right planet. What are some of the characteristics that make Earth unique among the planets? Consider the following. If Earth were considerably larger, its force of gravity would be proportionately greater. Like the giant planets, Earth might have retained a thick, hostile atmosphere consisting of ammonia and methane, and possibly hydrogen and helium. If Earth were much smaller, oxygen, water vapor, and other volatiles would escape into space and be lost forever. Thus, like the Moon and Mercury, both of which lack appreciable atmospheres, Earth would be devoid of life. If Earth did not have a rigid lithosphere overlaying a weak asthenosphere, plate tectonics would not operate. The continental crust would not have formed without the recycling of plates. Consequently, the entire planet would likely be covered by an ocean a few kilometers deep. As author Bill Bryson so aptly stated, there might be life in that lonesome ocean, but there certainly wouldn't be baseball. Most surprising, perhaps, is the fact that if our planet did not have a molten metallic outer core, most of the life forms on Earth would not exist. Fundamentally, without the flow of iron in the core, Earth could not support a magnetic field. It is the magnetic field that prevents lethal cosmic rays from showering Earth's surface and stripping away our atmosphere. A short history of nearly everything. The right location. One primary factor that determines whether a planet is suitable for higher life forms is its location in the solar system. The following scenarios substantiate Earth's advantageous position. If Earth were about 10% closer to the Sun, our atmosphere would be more like that of Venus and consist mainly of the greenhouse gas carbon dioxide. Earth's surface temperature would then be too hot to support higher life forms. If Earth were about 10% farther from the Sun, the problem would be reversed: it would be too cold. The oceans would freeze over, and Earth's active water cycle would not exist. Without liquid water, all life would perish. Earth is near a star of modest size. Stars like the Sun have a lifespan of roughly 10 billion years and emit radiant energy at a fairly constant level during most of this time. Giant stars, on the other hand, consume their nuclear fuel at very high rates and burn out in a few 100 million years. Therefore, Earth's proximity to a modest-sized star allowed enough time for the evolution of humans, who first appeared on this planet only a few million years ago. The right time. The last, but certainly not the least, fortuitous factor for Earth is timing. The first organisms to inhabit Earth were extremely primitive and came into existence roughly 3.8 billion years ago. From that point in Earth's history, innumerable changes occurred, life forms came and went, and the physical environment of our planet was transformed in many ways. Consider two of the many timely Earth-altering events. Earth's atmosphere has developed over time. Earth's primitive atmosphere is thought to have been composed mostly of nitrogen, water vapor, methane, and carbon dioxide, but no free oxygen, that is, oxygen not combined with other elements. Fortunately, microorganisms evolved that released oxygen into the atmosphere through the process of photosynthesis. About 2.5 billion years ago, an atmosphere with free oxygen came into existence. The result was the evolution of the ancestors of the vast array of multicellular organisms that we find on Earth today. About 66 million years ago, our planet was struck by an asteroid 10 kilometers in diameter. This impact likely caused a mass extinction during which nearly 3/4 of all plant and animal species were obliterated, including dinosaurs. Although this may not seem lucky, the extinction of dinosaurs opened new habitats for small mammals that survived the impact. These habitats, along with evolutionary forces, led to the development of the many large mammals that occupy our modern world. Without this event, mammals might have remained mostly small and inconspicuous. We use the term dinosaurs to refer to all members of this group except birds. Figure 19.2. Paleontologists uncover the remains of a 10-million-year-old rhinoceros at a dig site near Orchard, Nebraska. As various observers have noted, Earth developed under just right conditions to support higher life forms. Astronomers refer to this as the Goldilocks scenario. Like the classic Goldilocks and the Three Bears fable, Venus is too hot, Mars is too cold, but Earth is just right. Viewing Earth's history. The remainder of this chapter focuses on the origin and evolution of planet Earth, the one place in the universe we know fosters life. As you learned in Chapter 18, researchers utilize many tools to interpret clues about Earth's past. Using these tools, as well as clues contained in the rock record, scientists continue to unravel many complex events of the geologic past. This chapter provides a brief overview of the history of our planet and its life forms, a journey that takes us back about 4.6 billion years to the formation of Earth. Later, we will consider how our physical world assumed its present state and how Earth's inhabitants changed through time. As you read this chapter, refer to the geologic time scale presented in Figure 19.3. Numbers represent time in millions of years before the present. The Precambrian accounts for about 88% of geologic time. Figure 19.3 The geologic time scale. Figure 19.3 Full alternative text description. Did you know? The names of several periods on the geologic time scale refer to places that have prominent strata of that age. For example, the Cambrian period is taken from the Roman name for Wales. The Permian is named for the province of Perm in Russia, while the Jurassic period gets its name from the Jura Mountains located between France and Switzerland. Concept checks 19.1. 1. In what way is Earth unique among the planets of our solar system? 2. Explain why Earth is just the right size. 3. Why is Earth's molten, metallic core important to humans living today? 4. Why is Earth's location in the solar system ideal for the development of higher life forms? 19.2 Birth of a planet. Outline the major stages in Earth's evolution, from the Big Bang to the formation of our planet's layered internal structure. The universe began about 13.8 billion years ago with the Big Bang, when all matter and space came into existence. Shortly thereafter, the two simplest elements, hydrogen and helium, formed. These basic elements were the ingredients for the first star systems. Several billion years later, our home galaxy, the Milky Way, came into existence. It was within a band of stars and nebular debris in an arm of this spiral galaxy that the Sun and planets took form nearly 4.6 billion years ago. From the Big Bang to heavy elements. One of the products of the Big Bang was an array of subatomic particles, including protons, neutrons, and electrons. Later, as this debris cooled, these subatomic particles combined to generate atoms of hydrogen and helium, the two lightest elements. Within a few hundred million years, clouds of these gases condensed and coalesced into billions of stars that formed the first galactic systems. Ages are in billions of years. Smart Figure 19.4 Major events that led to the formation of early Earth. Smart Figure 19.4 Full alternative text description. Watch tutorial, Formation of Earth. As these gases contracted to become the first stars, heating triggered the process of nuclear fusion. Within the interiors of stars, hydrogen nuclei convert to helium nuclei, releasing enormous amounts of radiant energy. Astronomers have determined that in stars more massive than our Sun, other thermonuclear reactions occur, generating all the elements on the periodic table up to number 26, iron. The heaviest elements are created only at extreme temperatures during the explosive death of a star 8 or more times as massive as the Sun. During these cataclysmic supernova events, exploding stars produce all the elements heavier than iron and spew them into interstellar space. It is from such debris, as well as pre-existing gases, that our Sun and solar system formed. Based on the Big Bang scenario, all the atoms in your body except for hydrogen were produced billions of years ago, in the hot interior of now-defunct stars, and the gold in your jewelry was produced during a supernova explosion that occurred in some distant place. From planetesimals to protoplanets. Recall that the solar system, including Earth, formed about 4.6 billion years ago from the solar nebula, a large rotating cloud of interstellar dust and gas. As the solar nebula contracted, most of the matter collected in the center to create the hot protosun. The remaining materials formed a thick, flattened, rotating disk, within which matter gradually cooled and condensed into grains and clumps of icy, rocky, and metallic material. Repeated collisions resulted in most of the material eventually collecting into asteroid-sized objects called planetesimals. The composition of planetesimals was largely determined by their proximity to the protosun. As you might expect, temperatures were highest in the inner solar system and decreased toward the outer edge of the disk. Therefore, between the present orbits of Mercury and Mars, the planetesimals were composed mainly of materials with high melting temperatures, metals and rocky substances. The planetesimals that formed beyond the orbit of Mars, where temperatures are low, contained high percentages of ices, water, carbon dioxide, ammonia, and methane, as well as smaller amounts of rocky and metallic debris. Through repeated collisions and accretion, these planetesimals grew into 8 protoplanets, as well as dwarf planets and some larger moons. During this process, the same amount of matter was concentrated into fewer and fewer bodies, each having greater and greater masses. At some point in Earth's early evolution, a giant impact occurred between a Mars-sized object and a young, semi-molten Earth. This collision ejected huge amounts of debris into space, some of which coalesced to form the Moon. Earth's early evolution. As material continued to collide and accumulate, the high-velocity impacts of interplanetary debris and the decay of radioactive elements caused the temperature of our planet to steadily increase. This early period of heating resulted in a magma ocean that was perhaps several hundred kilometers deep. Within the magma ocean, buoyant masses of molten rock rose toward the surface and eventually solidified to produce thin rafts of crustal rocks. Geologists call this early period of Earth's history the Hadean, which began with Earth's formation about 4.6 billion years ago and ended roughly 4 billion years ago. The name Hadean is derived from the Greek word Hades, meaning the underworld, referring to the hellish conditions on Earth at the time. The Hadean is an unofficial eon of geologic time that occurred before the Archean. Its name refers to the hellish conditions on Earth. During the early Hadean, Earth had a magma ocean and experienced intense bombardment by nebular debris. Figure 19.5 Artistic depiction of Earth during the Hadean. During this period of intense heating, Earth became so hot that iron and nickel began to melt. Melting produced liquid blobs of heavy metal that sank toward the center of Earth under their own weight. This process occurred rapidly on the scale of geologic time and produced Earth's dense iron-rich core. As you learned in Chapter 9, the formation of a molten iron core was the first of many stages of chemical differentiation in which Earth converted from a homogeneous body, with roughly the same matter at all depths, to a layered planet with materials sorted by density. This period of chemical differentiation established the 3 major divisions of Earth's interior: the iron-rich core, the thin primitive crust, and Earth's thickest layer, the mantle, located between the core and the crust. In addition, the lightest materials, including water vapor, carbon dioxide, and other gases, escaped to form a primitive atmosphere and, shortly thereafter, the oceans. Concept checks 19.2. 1. What 2 elements made up most of the very early universe? 2. Name the cataclysmic event in which an exploding star produces all the elements heavier than iron. 3. Briefly describe the formation of the planets from the solar nebula. 4. Describe the conditions on Earth during the Hadean. 19.3 Origin and evolution of the atmosphere and oceans. Describe how Earth's atmosphere and oceans formed and evolved through time. We can be thankful for our atmosphere. Without it, there would be no greenhouse effect, and Earth would be nearly 60 degrees Fahrenheit colder. Earth's water bodies would be frozen nearly solid, making the hydrologic cycle non-existent. The air we breathe is a relatively stable mixture of 78% nitrogen, 21% oxygen, about 1% argon, and small amounts of other gases such as carbon dioxide and water vapor. However, our planet's original atmosphere was substantially different. Earth's primitive atmosphere. Early in Earth's formation, its atmosphere likely consisted of gases most common in the early solar system: hydrogen, helium, methane, ammonia, carbon dioxide, and water vapor. The lightest of these, hydrogen and helium, most likely escaped into space because Earth's gravity was too weak to hold them. The remaining gases, methane, ammonia, carbon dioxide, and water vapor, contain the basic ingredients of life: carbon, hydrogen, oxygen, and nitrogen. This early atmosphere was enhanced by a process called outgassing, through which gases trapped in the planet's interior are released. Outgassing from hundreds of active volcanoes still remains an important planetary function worldwide. However, early in Earth's history, when massive heating and fluid-like motion occurred in the mantle, the gas output would likely have been immense. These early eruptions probably released mainly water vapor, carbon dioxide, and sulfur dioxide, with minor amounts of other gases. Most importantly, free oxygen was not present in Earth's primitive atmosphere. Outgassing continues today from hundreds of active volcanoes worldwide. Figure 19.6 Outgassing produced Earth's first enduring atmosphere. Oxygen in the atmosphere. As Earth cooled, water vapor condensed to form clouds, and torrential rains began to fill low-lying areas,